January 28, 1922. Washington, D.C. At 9:13 p.m., during a sold-out showing of the silent film Get Rich Quick Wallingford, the roof of the Knickerbocker Theatre collapsed under the weight of accumulated snow. The steel beams supporting the ceiling buckled, twisted, and fell, bringing down tons of concrete, plaster, and timber onto the audience below. 98 people died instantly. 133 were injured. It remains the deadliest disaster in Washington, D.C. history. The collapse was not caused by an earthquake, a bombing, or defective materials. It was caused by snow. 28 inches of snow that had been falling for 3 days, piling up on a flat roof that was never designed to hold that much weight. But the real cause was deeper than weather. It was caused by an architect who ignored basic engineering principles, a builder who cut corners to save money, and a city that had no building codes to stop them. The Knickerbocker Theatre opened in October 1917, just 5 years before the collapse. It was built to be the most luxurious movie palace in Washington, a monument to the new art form of cinema. The building cost over $300,000, an enormous sum at the time. The exterior was decorated with white marble and ornate columns in the classical Greek style. The interior featured a grand lobby with crystal chandeliers, velvet curtains, and seats for nearly 1,800 people. The architect was Reginald Gere, a designer known for theaters and department stores. Gere was not a structural engineer. He understood how to make buildings look impressive, but he did not fully understand the mathematics of how weight is distributed through a structure. This distinction is critical. An architect designs how a building looks and functions. A structural engineer calculates whether the design will actually stand up. In modern construction, these are separate jobs performed by different professionals who check each other's work. In 1917, many architects, including Gere, designed structures without consulting engineers. They relied on intuition, experience, and rough calculations. Sometimes this worked. Sometimes it did not. The Knickerbocker Theatre had a flat roof. Flat roofs are common in commercial buildings because they are cheaper and easier to construct than sloped roofs. But flat roofs have a serious weakness. They do not shed snow. When snow falls on a sloped roof, like the roof of a house, gravity pulls the snow down the slope and it slides off. A sloped roof can only accumulate a limited amount of snow before it clears itself. A flat roof has no slope, so snow just piles up. The only way snow leaves a flat roof is by melting or being manually removed. If snow keeps falling and the temperature stays below freezing, the accumulation can become enormous. To understand the problem, you need to understand how much snow weighs. Fresh, fluffy snow weighs about 5 to 10 pounds per cubic foot. That does not sound like much. But snow accumulates in layers. Each new layer compresses the layers beneath it, squeezing out the air and making the snow denser. Compressed snow can weigh 20 to 30 pounds per cubic foot. Wet snow, which has a high water content, can weigh 40 to 50 pounds per cubic foot. A flat roof covered with 2 feet of wet snow is supporting an additional 40 to 60 pounds per square foot across its entire surface. For a large building, this adds up to hundreds of thousands of pounds. The roof of the Knickerbocker Theatre was approximately 11,000 square feet. If that roof was covered with 2 feet of snow weighing 50 pounds per cubic foot, the total weight would be over 1 million pounds. That is 500 tons of snow sitting on a structure designed to hold the weight of the roof itself, plus maybe a few maintenance workers. Reginald Gere designed the roof using a construction method common at the time called flat slab concrete with steel trusses. Here is how it worked. Steel beams were installed horizontally, spanning from one wall to the other. These beams, called joists, were spaced a few feet apart and supported by vertical steel columns. On top of the joists, wooden planks were laid to create a flat surface. On top of the planks, a layer of concrete was poured to create a solid, weatherproof roof. The concrete was reinforced with steel rods, which made it stronger. This design works well if the steel beams are strong enough and properly spaced. The problem was that Gere underestimated how much weight the roof would need to support. His calculations assumed the roof would only need to hold its own weight, called the dead load, plus occasional additional weight from maintenance workers or equipment, called the live load. He calculated the dead load correctly. The concrete, steel, and wood together weighed approximately 50 pounds per square foot. He estimated the live load at 20 pounds per square foot, which is standard for a roof that people do not regularly walk on. So his design was built to support 70 pounds per square foot total. But he made a critical error. He did not account for snow load. Snow load is the additional weight that a roof must support when snow accumulates. In regions where it snows regularly, building codes require roofs to be designed for a specific snow load based on historical weather data. In Washington, D.C., where the Knickerbocker was built, heavy snow was rare but not unheard of. A conservative design would have assumed a snow load of at least 30 to 40 pounds per square foot. Gere assumed 0. He later claimed he believed the roof would be shoveled after snowstorms, so snow would never accumulate. This assumption was insane. The Knickerbocker had a flat roof 50 feet above the ground with no easy access. There was no hatch, no external staircase, and no platform for workers to stand on. Shoveling the roof would require scaffolding or a crane, which would take hours to set up. No one was going to shovel the roof. But even if Gere had accounted for snow load, there was another problem. The steel trusses supporting the roof were undersized. A truss is a framework made of steel beams arranged in triangles. Triangles are extremely strong shapes because they distribute weight evenly across all three sides. A properly designed truss can support enormous loads without bending. The Knickerbocker's trusses were not properly designed. The beams were too thin, and the connections between beams were too weak. The construction company, Harry Braloff Company, had been hired because they submitted the lowest bid. They saved money by using cheaper, lighter steel than the design specified. Instead of using steel beams with a thickness of ½ inch, they used beams that were 3/8 of an inch thick. This sounds like a small difference, but in structural engineering, small differences matter. A beam that is 3/8 of an inch thick is significantly weaker than a beam that is ½ an inch thick. The strength of a steel beam is proportional to its cross-sectional area.
January 27, 1922. A low-pressure weather system moved up the Atlantic coast and stalled over the mid-Atlantic region. Meteorologists, using the limited technology available in 1922, predicted snow but underestimated the storm's intensity. It would later be called the Knickerbocker Storm, named after the theater it destroyed. The snow began falling on the morning of January 27th and did not stop for nearly 3 days. By the evening of January 28th, 28 inches of snow had fallen on Washington, D.C., the largest single-storm snowfall the city had ever recorded. The snow was not light and fluffy. It was heavy and wet, the kind of snow that is difficult to shovel because it clumps together and sticks to everything. Wet snow forms when the temperature is close to freezing, around 32 degrees Fahrenheit. The snow melts slightly as it falls, and the water content increases. This makes the snow much heavier. Meteorologists estimate that the snow on the Knickerbocker's roof weighed between 40 and 60 pounds per cubic foot, depending on depth and compression. With 28 inches of accumulation, the roof was supporting approximately 70 to 100 pounds per square foot of snow. Remember, the roof was designed to hold 70 pounds per square foot total, including its own weight. The snow alone exceeded the design capacity. The steel beams were being asked to hold more weight than they were designed for. Steel is strong, but it is not infinitely strong. When you load a steel beam beyond its capacity, it does not break immediately. First, it bends. The technical term is elastic deformation, which means a beam bends but will return to its original shape if the load is removed. If the load continues to increase, the beam reaches a point called the yield strength, where it begins to deform permanently. The beam bends and stays bent even if the load is removed. If the load increases further, the beam reaches its ultimate strength and fails catastrophically, either by snapping in half or by buckling, which is when the beam suddenly folds sideways like a collapsing accordion. The beams supporting the Knickerbocker's roof reached their yield strength sometime on the afternoon of January 28th. Workers in the theater's projection booth, which was located just below the roof, reported hearing popping and creaking sounds throughout the day. These sounds were the steel beams bending and the rivets holding them together beginning to shear. Rivets are metal pins that hold steel beams together. They are driven through holes in the beams and hammered flat on both ends to lock the beams in place. Rivets are strong, but when a beam bends, the rivets experience shearing force, which means they are being pushed sideways. If the force is strong enough, the rivet snaps. On the evening of January 28th, the Knickerbocker was showing the film Get Rich Quick Wallingford, a comedy based on a popular play. The theater was nearly full. Approximately 900 people were in the audience, including many families with children. The movie had started at 8:30 p.m. By 9 p.m., the film was about halfway through. The audience was laughing, eating popcorn, and enjoying the show. They had no idea the roof was failing above them. At approximately 9:10 p.m., a loud crack echoed through the theater. Some people in the audience heard it and looked up. Others thought it was part of the movie's sound effects. Silent films in 1922 were not actually silent. They were accompanied by live music from an orchestra or a piano, and sometimes sound effects were added by crew members backstage. The crack was followed by a grinding, groaning sound, like metal being twisted. This was the sound of the steel trusses buckling. At 9:13 p.m., the roof collapsed. It did not fall all at once. The failure began at the center of the roof, where the load was greatest. One of the main steel trusses buckled, folding in the middle like a broken stick. The concrete slab it was supporting, which weighed several tons, dropped approximately 6 inches. This sudden movement shifted the load onto the adjacent trusses, which were already overstressed. They buckled immediately. The failure propagated outward in a chain reaction. One truss failed, then the next, then the next. The entire process took less than 5 seconds. The concrete roof slab, no longer supported, broke into massive chunks and fell. Each chunk weighed several tons. They crashed through the theater's ornate plaster ceiling, which shattered into clouds of dust and debris. The steel beams followed, twisting and falling like giant pieces of metallic spaghetti. Witnesses outside the theater described hearing an explosion-like sound, followed by a rumble that lasted several seconds. The entire building shook. Dust and snow billowed out of the shattered windows. Inside, the scene was apocalyptic. The falling debris hit the balcony first, collapsing it onto the orchestra seating below. People in the balcony were crushed instantly. Those in the orchestra seats were buried under tons of concrete, steel, and timber. The theater's ornate chandelier, which weighed over 2,000 pounds, fell and crushed several rows of seats. People who survived the initial collapse found themselves trapped in darkness. The electrical system had been severed, and all the lights went out. The emergency exits were blocked by debris. Dust filled the air, making it difficult to breathe or see. Some people were buried up to their necks in rubble, able to move their heads but unable to free their bodies. Others were pinned under beams, their limbs crushed. The screaming was constant, a chorus of pain and terror. Outside, people heard the collapse and ran to help. The first rescues arrived within minutes. They were ordinary citizens, people who had been walking past the theater or dining in nearby restaurants. They began pulling at the rubble with their bare hands, lifting chunks of concrete and timber, searching for survivors. The Washington Fire Department arrived 15 minutes after the collapse. Firefighters brought saws, crowbars, and ropes. They worked through the night in sub-zero temperatures, cutting through steel beams, lifting debris, and pulling victims from the wreckage. The rescue was complicated by the instability of the remaining structure. The walls were still standing, but they were cracked and leaning. More debris could fall at any moment. Firefighters worked in teams, with some holding up sections of collapsed roof while others crawled underneath to reach victims. Survivors described being trapped for hours, hearing rescuers working nearby but unable to call out because they were too weak or their mouths were full of dust. Some were rescued after 6 or 7 hours. Others were found dead, having suffocated or bled to death while waiting. The final victim was pulled from the wreckage at 4 a.m. on January 29th, nearly 7 hours after collapse. 98 people were confirmed dead. 133 were injured, many critically. The bodies were taken to a temporary morgue set up in a nearby building. The death toll included entire families. One of the victims was Congressman Andrew Jackson Botchfeld of Pennsylvania, who had brought his wife and children to see the movie. All 4 died. Another victim was Captain Claude Ramsey, a U.S. Army officer, who died shielding his wife with his body. She survived with serious injuries. January 29th, 1922. The morning after the collapse, Washington, D.C. was paralyzed. The streets were buried under 2 feet of snow. The collapsed theater was the lead story in every newspaper in the country. The headlines asked the same question: how could this happen? The city immediately convened an investigation. The District of Columbia Board of Inquiry was tasked with determining the cause of the collapse and assigning responsibility. The investigation lasted months and heard testimony from dozens of witnesses, including architects, engineers, construction workers, and survivors. The findings were damning. The inquiry determined that the collapse was caused by a combination of factors. First, the roof was not designed to support the weight of heavy snow. Architect Reginald Gear had failed to include snow load in his calculations. Second, the steel trusses were undersized and improperly constructed. The construction company, Harry Barlow Company, had used thinner steel than specified and had installed the trusses incorrectly, with inadequate connections at critical joints. Third, the city had failed to enforce building codes. Inspectors had approved the building without verifying that the roof could support expected loads. The inquiry recommended criminal charges against Gear and the officers of the Barlow Company. They were charged with manslaughter. The trial was a public spectacle. Reginald Gear took the stand and admitted he had not calculated snow load. He claimed this was standard practice in 1917 and that he had relied on the builder to use appropriate materials. He argued that the collapse was caused by an unusually heavy storm, not by design flaws. The jury did not believe him. Gear was found guilty of criminal negligence. He was fined $5,000 and his architectural license was revoked. He never designed another building. He died in obscurity in 1929, his reputation destroyed. The officers of the Barlow Company were also found guilty. They were fined and barred from bidding on government contracts. The company went bankrupt shortly after, but the investigation revealed a deeper problem. Washington, D.C. in 1922 had virtually no enforceable building codes. The city had basic regulations, but they were vague and rarely enforced. Inspectors had no authority to stop construction if they found problems. Builders could ignore their recommendations without consequence. The Knickerbocker collapse changed this. Within months, the District of Columbia passed comprehensive building codes based on standards developed by engineering organizations. The new codes required that all structures be designed by licensed engineers. Architects could design the appearance of buildings, but engineers had to verify the structure would stand. The codes also required specific design standards for roofs, including mandatory snow load calculations. In Washington, D.C., roofs were required to support at least 30 pounds per square foot of snow, even if the roof was flat and difficult to access. These regulations were revolutionary at the time. They established the principle that building safety is not optional, that structures must be designed to withstand predictable loads like snow, wind, and earthquakes, and that the government has a responsibility to enforce these standards. The impact extended beyond Washington. Cities across the United States examined their building codes and found them inadequate. Many had no codes at all. In the years following the Knickerbocker collapse, states and cities passed laws requiring building permits, inspections, and design standards. The concept of a building code, a set of enforceable rules governing how structures must be built, became universal. The collapse also changed how engineers think about load calculations. Before Knickerbocker, many designers used simple rules of thumb based on experience. After Knickerbocker, engineers began using more rigorous mathematical methods to calculate loads and stresses. The field of structural engineering became more scientific, more precise, and more conservative. One of the most important changes was the introduction of safety factors. A safety factor is a multiplier used in design to ensure structures are stronger than they need to be. For example, if a roof is expected to support 50 pounds per square foot, an engineer might design it to support 100 pounds per square foot, giving it a safety factor of 2. This provides a margin for error and accounts for unexpected loads. Modern building codes require safety factors for all structural elements. Roofs in snowy regions are designed to support several times the expected snow load. Bridges are designed to hold far more weight than they will ever carry. Buildings in earthquake zones are designed to withstand forces greater than the largest recorded earthquake. These safety factors exist because of disasters like Knickerbocker. The human stories from the collapse stayed with Washington for generations. One of the most heartbreaking was the story of the Ruffner family. Dr. Sterling Ruffner, a prominent physician, had taken his wife and 2 daughters to see the movie. All 4 died. Their funeral was attended by thousands. Another story was that of firefighter Thomas Hagen, who pulled 12 people from the wreckage before a secondary collapse injured him severely. He survived but never fully recovered from his injuries. He was awarded the Carnegie Medal for heroism. The families of the victims filed lawsuits against the theater owner, the architect, and the builder. The cases dragged through courts for years. Most families received small settlements, often less than $5,000 per death. The theater owner declared bankruptcy, and the building was demolished. The site remained empty for years, a vacant lot covered with snow each winter, a reminder of the tragedy. In 1932, a small apartment building was constructed on the site. There is no marker or plaque commemorating the Knickerbocker Theatre. Most people walking past the location today have no idea what happened there. But the legacy of the collapse is everywhere. Every building code, every snow load calculation, every structural engineer checking an architect's design, every safety factor built into a roof or bridge exists because 98 people died under 2 feet of snow. The Knickerbocker Theatre collapse was not caused by an act of God. It was not an unforeseeable accident. It was caused by an architect who did not calculate snow load, a builder who used cheap materials, and a city that did not enforce safety standards. It was preventable. The victims died so that future generations would not. That is the legacy. That is why the story must be told. On January 28, 1922, at 9:13 p.m., 98 people went to see a movie and never came home. The snow fell, the roof fell, and the laws changed forever.